On the first day of 1995, an oil platform sitting in the North Sea recorded something that should not have existed. The surrounding waves were rough but unremarkable. Nothing unusual on the instruments, nothing to suggest what was coming. Then a single wave arrived, 25 meters tall. That is the height of an 8-story building, moving toward you at highway speed, appearing out of open water with no warning, no buildup, no time to do anything at all. It lasted seconds, then it was gone, and it changed everything, because before that wave was recorded, the official position of science was simple. Waves like this do not happen. The mathematics of the ocean said they were so improbable, they could essentially be ruled out. When sailors returned from voyages describing walls of water rising out of nowhere in calm seas, waves that swallowed ships whole and left no survivors, those accounts were filed away as myth, exaggeration, the kind of story men tell when they need to explain what they cannot. The ocean, science insisted, behaved within limits. Then the instruments disagreed. That single recorded wave, now called the Dropner wave, did not just confirm that rogue waves were real, it revealed something far more unsettling. If one wave this size could appear undetected in a monitored location, how many had gone unrecorded? How many ships logged as lost in a storm had actually met something like this in otherwise normal conditions? The answer, when researchers started looking, was deeply uncomfortable. Rogue waves are not freak events. They are not rare anomalies. They appear to be a feature of the ocean that the entire field had simply failed to account for, and the ships we have been building for decades were never designed to survive one. So how does the ocean produce something like this? Where do these waves come from? And why, even now, can we still not reliably predict them? Tonight, we move into that uncertainty and take a closer look at one of the ocean's most unpredictable and least understood phenomena. But before we begin, tell me where you're listening from and what time it is for you right now. I always enjoy seeing where these videos reach, and if you'd like to support the channel, a like and subscribe goes a long way. Now let's begin. Across the open surface, motion begins as a transfer, so subtle it can pass unnoticed. Air moves first, sliding over water with a difference in speed that creates friction at the boundary between the two. That friction does not push the ocean forward in a single mass. Instead, it lifts small ripples, delicate rises that catch more wind as they form. Each slight elevation exposes a larger surface to the air, allowing more energy to pass downward. What begins as texture becomes movement, and movement gathers into form. As wind continues across distance, these early ripples grow into organized waves. Their size depends not only on wind speed, but on how long the wind has been blowing and how far it has traveled without interruption. This stretch of open water, known among oceanographers as fetch, allows energy to accumulate gradually. Over time, waves settle into patterns that reflect the conditions that shaped them. They travel in groups, not as isolated peaks, but as sequences where larger and smaller forms follow one another in a steady rhythm. Within these groups there is structure. A series of waves may rise and fall with a quiet regularity, their heights distributed in a way that can be measured and described. Most waves do not reach extremes. Instead, they cluster around an average, with only a few rising significantly above or falling below that range. This distribution allows the ocean, despite its constant motion, to be understood through probability. Patterns repeat often enough that they can be anticipated, not in exact detail, but within a range of expectation. This is where statistical models begin to take shape. By observing thousands of waves over time, researchers can describe the ocean in terms of likelihoods rather than certainties. The surface becomes a field of data, where each rise and fall contributes to a broader understanding of behavior. These models do not track individual waves as fixed objects. They describe conditions, tendencies, and limits. Within those limits, most of the ocean's motion remains contained. A central measure within this framework is known as significant wave height. It does not refer to a single wave, but to an average derived from the tallest portion of a wave group. Specifically, it represents the mean height of the highest third of waves observed over a given period. This method reflects how the sea is experienced in practice, since the most prominent waves shape perception more strongly than the smaller ones between them. By focusing on this upper range, the measure provides a stable way to describe conditions without being distorted by rare extremes. From this perspective, the ocean appears governed by balance. Energy enters through wind, spreads across the surface, and organizes into forms that follow predictable relationships. Larger waves carry more energy, but they remain part of a system where size and frequency are linked. As wave height increases, the number of such waves decreases. The surface becomes a shifting landscape, yet one that holds to patterns that can be studied and understood. Even in rough conditions, this structure persists. Waves may grow steeper and closer together, their crests breaking into foam, but their distribution still aligns with the underlying model. The sea does not move randomly. It follows principles shaped by physics, where energy disperses, interacts, and redistributes over time. Beneath the apparent disorder, there is continuity, a quiet consistency that defines how the ocean usually behaves. Long before instruments traced the surface in numbers, knowledge of the sea moved through voices carried from one voyage to the next. Accounts were exchanged in harbors, written into logs, or spoken quietly between those who had returned and those preparing to leave. Among these recollections were moments that resisted ordinary description, fragments of experience where the ocean seemed to gather itself into a single overwhelming form. Sailors described sudden elevations that rose beyond the surrounding sea, not as part of a sequence, but as something set apart. The language they used often reached for familiar structures, calling them walls, cliffs, or moving horizons, shapes that suggested solidity rather than motion. These forms appeared without warning, interrupting otherwise steady conditions, and passed just as quickly, leaving little behind except damage or absence. The descriptions varied in detail, yet shared a similar outline, a solitary rise that exceeded what the rest of the water seemed capable of producing. In many cases, these reports came without supporting evidence. A vessel might vanish along a known route, its loss attributed to weather or navigation, with no surviving account to explain what occurred. When stories did return, they were often carried by individuals who had witnessed something difficult to reconcile with expectation. Their accounts existed at the edge of what could be confirmed, shaped by memory and retelling, and therefore treated with caution by those seeking consistency. At the time, the understanding of ocean behavior rested on patterns that appeared stable and measurable. The sea was studied through averages, distributions, and recurring forms that could be observed across many conditions. Within this framework, extreme deviations were considered possible in theory, yet so unlikely that they held little practical weight. A wave rising far beyond its surroundings, standing alone without gradual formation, did not fit within the established range of behavior. Because of this, early reports of such events were often interpreted through a different lens. They were seen as exaggerations shaped by stress, or as misinterpretations of known phenomena observed under difficult conditions. The open ocean presents limited reference points, and perception can shift when scale becomes uncertain. Without instruments to confirm precise measurements, even experienced observers could struggle to describe what they had seen in terms that aligned with accepted models. Over time, a quiet divide formed between lived experience and scientific description. On one side were those who navigated the sea directly, accumulating knowledge through repeated exposure to its variations. On the other were those who studied it through collected data, building models that relied on consistency across many observations. Both perspectives sought to understand the same environment, yet they approached it from different forms of evidence, one rooted in individual encounter, the other in aggregated measurement. This difference did not imply dismissal of all seafaring knowledge, but it shaped which accounts were given weight. Reports that aligned with existing models reinforced confidence in those models, while those that did not were set aside as anomalies or uncertainties. The absence of reliable measurement tools for capturing extreme short-lived events meant that certain experiences remained unverified, existing in a space where they could be acknowledged, but not fully integrated into scientific understanding. As these narratives accumulated, they formed a scattered record of encounters that hinted at behavior beyond established expectations. They lingered in journals and oral histories, neither fully accepted nor entirely discarded, waiting within the margins of knowledge, where observation had reached further than explanation. In the quiet discipline of early ocean science, certainty was built from what could be measured, recorded, and repeated. Instruments defined the boundary of trust. What they captured formed the foundation of understanding, and what they could not capture remained outside it, unresolved and often set aside. The surface of the sea, vast and shifting, was reduced to points of observation, each one offering a narrow window into a much larger system. Measurement itself was constrained by both location and time. Fixed instruments were rare, often attached to buoys or coastal stations, limited in number and scattered across immense distances. Ships provided additional data, but their observations depended on human recording, shaped by motion, visibility, and interpretation. Even when measurements were precise, they represented only brief moments within a continuous process. The ocean did not pause for observation, and much of its behavior unfolded between these isolated records. Within this framework, patterns began to emerge, not from direct tracking of every wave, but from accumulated samples. Over time, these samples revealed distributions that appeared stable, where most wave heights clustered within a predictable range. Statistical models grew from this consistency, describing the likelihood of different wave sizes based on observed data. These models did not require every possibility to be measured directly. Instead, they extended known patterns into estimates of what was likely and what was not. As these models developed, they introduced a way of expressing rarity. Events could be assigned return periods, not as precise predictions, but as indications of how often something might occur within a given time frame. A wave described as occurring once in 10,000 years was not expected to appear on a schedule. It represented an event so far outside the common range that, within practical observation, it could be treated as nearly impossible. This concept provided a sense of boundary, a way to define the limits of expectation. Yet these limits were shaped by the data available. If the recorded range of wave heights remained within certain bounds, the models would reflect that range, reinforcing the idea that extremes beyond it were exceedingly rare. The absence of recorded events became part of the reasoning itself. What had not been measured was assumed to be negligible, not because it was proven absent, but because it had not appeared within the collected data. This created a quiet circularity. Instruments recorded typical behavior. Models described that behavior, and those models then framed what was considered possible. Reports that suggested conditions beyond those limits encountered a form of resistance, not through direct contradiction, but through incompatibility with established probability. Without measurements to support them, such accounts remained outside the accepted structure. The limitations of early tools also meant that brief, localized events could pass entirely unnoticed. A wave rising and falling within seconds, occurring far from observation points, would leave no trace in the record. Even if such events were not isolated, their transient nature made them difficult to capture. The ocean's surface, in constant motion, allowed for moments that existed fully yet left little evidence behind. In this environment, belief became tied to visibility within data. The unseen carried less weight, not from dismissal, but from the absence of confirmation. Scientific understanding advanced through what could be consistently observed, and in doing so, it established boundaries that reflected both knowledge and limitation. Within those boundaries, the ocean appeared to behave within defined limits, its extremes constrained by probability, its surface described by patterns that seemed complete, yet quietly depended on what had yet to be observed. On a winter morning in the North Sea, far from shore and held in place by steel anchored deep below, a platform stood surrounded by moving water that followed its usual, measured rhythm. The structure itself was designed to endure, its instruments quietly tracking the surface beyond its legs, converting motion into numbers that could be stored and examined. Nothing in the conditions suggested a departure from what had been observed countless times before. Among those instruments was a laser sensor directed downward, continuously measuring the distance between the platform and the passing sea. Each rise and fall translated into a precise record, a continuous line of data that reflected the shifting surface. The surrounding waves moved with a consistency that aligned with expectation, their heights and spacing fitting comfortably within the established range described by existing models. Then, within that stream of measurements, a single peak appeared. It rose sharply above the sequence that preceded it, standing apart not as a gradual increase, but as an abrupt deviation. The recorded height reached approximately 25 meters from trough to crest, far exceeding the surrounding waves, which remained within a much lower range. The shape of the event was distinct, a steep ascent followed by a rapid descent, captured in full by the instrument before returning to the pattern that had been present before it. This moment, later named the Dropner wave, was not observed through interpretation or recollection. It existed as a direct measurement, recorded with precision and preserved as data. The platform had not shifted position, the instrument had not failed, and the conditions around it remained consistent. The event was contained within a reliable system, leaving little room for ambiguity in its existence. What made this measurement significant was not only its size, but its context. According to prevailing statistical models, a wave of that magnitude should have been extraordinarily unlikely within the observed conditions. The distribution of wave heights suggested that such an event would occur on timescales far beyond practical observation. Yet here it was, appearing within a data set collected over a relatively short period, without preceding indicators that would suggest its arrival. The data itself carried a quiet authority. It did not argue or interpret. It simply presented what had occurred. Researchers examining the record could trace the sequence leading up to the event, observe the peak, and follow the return to normal conditions. The continuity of the measurement reinforced its validity, showing that the system had captured the ocean's behavior without interruption. As this record circulated through the scientific community, it introduced a point of tension between expectation and observation. Models that had been built on extensive data now faced a result that did not align with their predictions. The discrepancy did not immediately overturn those models, but it revealed a gap within them, a space where the ocean's behavior extended beyond what had been accounted for. The Dropner measurement did not stand entirely alone for long. As attention turned toward identifying similar events, other records began to surface, some from satellite observations, others from additional fixed platforms. These findings suggested that the event was not an isolated anomaly, but part of a broader pattern that had previously gone unrecognized. In this way, the significance of that single recorded wave extended beyond its moment of occurrence. It marked a transition from uncertainty to confirmation, where an event once considered nearly impossible had been captured within reliable measurement. The ocean, as it was understood through data, now carried evidence of behavior that required a deeper examination, not as an exception to be dismissed, but as a feature to be understood within the evolving picture of its dynamics. There are moments in science when a single line of data sits quietly against everything that came before it, not dramatic in appearance, yet impossible to reconcile. The record from that winter morning carried this quality. It did not resemble noise or error, nor did it align with the smooth distributions that had defined ocean behavior for decades. It stood within the dataset as something both precise and unaccounted for. The established models described the sea through probability, where wave heights followed a predictable spread around an average. In this framework, extreme values were not excluded, but their likelihood diminished rapidly as size increased. The mathematics shaped a curve where the tallest waves were rare, and those far beyond the typical range became vanishingly improbable. Within such a system, the expectation of a single wave rising to that measured height, surrounded by much smaller waves, was effectively negligible. Yet, the recorded sequence showed continuity. The surrounding measurements remained consistent with known patterns, forming a baseline that reinforced the validity of the system. Then, within that continuity, the peak appeared, not as part of a gradual escalation, but as a sudden deviation that exceeded the statistical envelope. It was not simply larger than expected, it existed outside the assumptions that defined what was expected at all. This discrepancy did not suggest that the data was flawed. Instead, it pointed toward a limitation in the model itself. The mathematical descriptions had been built on the premise that wave interactions produced distributions that remained stable over time. They accounted for variation, but within bounds shaped by linear superposition, where individual waves combined without fundamentally altering each other's behavior. The Dropner measurement hinted at processes that did not follow this simplicity. As researchers examined the event more closely, attention shifted toward mechanisms that could concentrate energy in ways not fully represented in earlier models. Nonlinear effects, where waves influence each other beyond simple addition, began to take on greater importance. In such conditions, energy does not disperse evenly across the surface. Instead, it can momentarily gather, forming peaks that rise disproportionately above their surroundings before dissolving back into the broader field. This realization introduced a subtle but profound change in perspective. The ocean was no longer seen solely as a system governed by averaged behavior and gradual variation. It also contained pathways for sudden amplification where local conditions could produce outcomes far beyond what the overall statistics would suggest. These pathways did not dominate the system, but they existed within it, embedded in the interactions that occurred continuously across the surface. The models that followed began to incorporate these complexities, though not all at once. Adjustments were made to include nonlinear dynamics, wave focusing, and the influence of underlying currents. Each addition expanded the range of possible behavior, allowing for events that had previously been considered too rare to matter. The ocean's statistical description became less rigid acknowledging that extremes were not merely distant outliers, but part of the system's inherent variability. Even so, the transition was gradual. Established frameworks do not dissolve immediately, especially when they have successfully described most observed conditions. Instead, they evolve, absorbing new evidence while maintaining continuity with what has already been understood. The Dropner wave became a reference point within this process, a measured instance that anchored the shift from assumption to revision. In the quiet language of data, it marked a boundary where certainty gave way to a broader understanding. The surface of the ocean, once framed by limits that seemed well-defined, now revealed a capacity for behavior that extended beyond those limits, not as an exception, but as an integral part of its nature. A single crest can pass across the open sea without drawing attention, its height absorbed into the broader motion that surrounds it. What defines a rogue wave begins not with its absolute size, but with how it relates to everything nearby. The surface may carry many waves at once, each rising and falling within a shared rhythm, yet a rogue event separates itself from that rhythm in a way that becomes unmistakable when measured against its immediate context. The defining threshold is relative rather than fixed. A wave is considered rogue when its height exceeds twice that of the significant wave height present at the time, placing it far beyond the upper range of the surrounding field. This comparison anchors the definition to local conditions, meaning that the same physical height might be ordinary in one setting and extraordinary in another. It is the contrast, not the isolated measurement, that gives the event its identity. Within a typical wave group, peaks and troughs follow one another with gradual variation. Larger waves appear, but they do so as part of a sequence, rising slightly above their neighbors while still belonging to the same overall structure. The surface retains a sense of continuity where no single wave dominates the entire field. A rogue wave disrupts this continuity. It does not emerge as the highest point in a smooth progression, but as a sudden elevation that stands apart, surrounded by comparatively smaller forms. This separation creates a visual and physical distinction. The rogue wave appears as an isolated feature, often preceded and followed by waves that do not approach its scale. The lack of buildup contributes to its defining character. Rather than forming through a gradual increase in energy across multiple waves, it rises sharply within a localized region, concentrating height into a single crest that does not extend into a broader pattern. The importance of contrast becomes clearer when considering how waves are experienced. A vessel moving through a field of large but consistent waves adjusts to that environment, its motion responding to the regular spacing and height. When a rogue wave appears, it introduces a discontinuity in that experience. The surrounding conditions provide no indication of the scale that is about to be encountered, and the difference between expectation and reality becomes part of what defines the event. From a scientific perspective, this emphasis on relative height allows rogue waves to be identified across different sea states. In calmer conditions, a smaller, absolute wave can meet the criteria if it significantly exceeds the local average. In rougher seas, a much larger wave may still be considered typical if it aligns with the surrounding distribution. The definition remains consistent because it is tied to proportion rather than magnitude alone. This proportional approach also reflects the underlying processes that give rise to such waves. The ocean's surface is a field of interacting energies, where local conditions can vary even within a seemingly uniform area. When those interactions produce a concentration of energy in one place, the result is not just a taller wave, but a wave that diverges from the structure around it. Its identity is shaped by this divergence, by the way it stands outside the pattern that defines the rest of the surface. In this sense, a rogue wave is less about scale and isolation and more about deviation within context. It is a moment where the surface departs from its own rhythm, where one crest carries a height that cannot be anticipated by observing the waves that surround it, and where contrast becomes the defining feature of its presence. At any given moment, the surface is not shaped by a single motion, but by many, each arriving from a different place, carrying its own rhythm, direction, and history. These motions pass through one another continuously, overlapping without losing their identity, forming a layered field where patterns are never fixed. What appears smooth from a distance is, at a finer scale, a meeting point of countless moving influences. Each wave travels with a certain frequency and wavelength, shaped by the conditions that created it. Some are long and widely spaced, moving with a steady, measured rise. Others are shorter, more tightly grouped, crossing the surface at different angles. When these waves intersect, they do not collide in the way solid objects would. Instead, they combine, their heights adding together at each point of contact, then separating again as they continue on their paths. This process, known as interference, governs much of the ocean's surface behavior. In most cases, the interaction produces only small variations, slight increases or decreases that blend into the overall motion. A crest may rise a little higher when it meets another, then return to its previous form as the waves move apart. The surface remains dynamic, yet balanced, with energy distributed across many overlapping patterns. There are moments, however, when this interaction becomes more focused. If several waves align in such a way that their crests meet at the same place and time, their combined height can increase significantly. This is called constructive interference, a condition where individual contributions reinforce one another rather than cancel out. The resulting peak is not a new wave formed from a single source, but a temporary convergence of energy from multiple directions. This convergence does not last long. The waves involved continue to move, each following its own path, and the alignment that produced the peak dissolves as quickly as it formed. The energy disperses back into the surrounding field, returning to the broader pattern of overlapping motions. What remains is a brief amplification, a moment where the surface rises beyond its immediate surroundings before settling again into continuity. The likelihood of such alignment depends on the complexity of the wave field. In regions where waves travel from multiple directions, with varying frequencies and phases, the opportunities for constructive interference increase. Most of these interactions produce only modest changes, but under certain conditions, the alignment becomes more precise, allowing energy to gather more fully into a single location. This perspective shifts the understanding of the surface from a collection of independent waves to a continuous interplay of moving forms. The ocean is not a flat plain disturbed by isolated peaks, but a dynamic system where motion is shared, exchanged, and redistributed across space. Each point on the surface reflects the combined influence of many waves, interacting in ways that are both structured and variable. Within this system, a larger peak can emerge without requiring a single wave to grow beyond its origin. Instead, it arises from the momentary cooperation of several waves, each contributing to a shared elevation. The height of that peak is not carried forward as a permanent feature, but exists only within the alignment that created it. Once that alignment shifts, the peak dissolves, leaving no lasting trace except in the memory of the motion itself. In this way, the ocean reveals a subtle complexity where the appearance of a single, pronounced rise can be understood as the result of many smaller motions working together, briefly and precisely, before continuing on their separate paths. There are intervals when motion across the surface begins to gather rather than disperse, as if the usual spreading of energy pauses and turns inward. The surrounding waves continue their passage, yet within a small region, their influence starts to overlap in a way that alters the balance. The change is not visible at first as a single rising form, but as a tightening of movement, where distances between crests shorten and the surface appears to draw itself together. Energy within a wave is not confined to its crest alone. It extends through the water column, carried in orbital motions that move both upward and forward. Under typical conditions, this energy distributes across many waves, each one carrying a portion that contributes to the overall pattern. The surface maintains a kind of equilibrium where no single location holds a disproportionate share for long. Yet this balance is not fixed. It can shift when interactions begin to favor concentration over dispersion. In certain circumstances, waves influence one another in ways that go beyond simple addition. Their shapes begin to change as they interact, becoming steeper and more compact. This behavior reflects a nonlinear process where the presence of one wave alters the properties of another, allowing energy to transfer unevenly between them. Instead of remaining evenly spread, energy can be drawn into specific regions, intensifying the motion there while leaving surrounding areas relatively unchanged. As this concentration develops, the surface begins to rise more sharply. The crest that forms is narrower, its sides steeper, and its height increasing at a rate that does not match the broader field. The wave no longer resembles the smoother forms that dominate under stable conditions. It carries a sense of compression, as though the energy within it has been gathered from a wider area and brought into a single point. This process is influenced by several factors, including the alignment of waves, their relative speeds, and the depth of the water beneath them. When waves travel at slightly different velocities, faster ones can overtake slower ones, merging their energy in the process. If this merging occurs repeatedly within a confined region, the effect becomes cumulative. Each interaction adds to the concentration, allowing the crest to grow more pronounced with each passing moment. Water depth plays a quiet role as well. In deeper regions, waves can maintain their structure over longer distances, preserving the conditions that allow these interactions to occur. The energy remains less constrained by the seafloor, enabling it to move and reorganize more freely. This freedom allows localized concentrations to develop without being quickly dissipated by external influences. Despite this buildup, the state is inherently temporary. The forces that bring energy together are balanced by those that pull it apart. As the concentrated crest reaches its peak, the underlying interactions begin to shift. The alignment that supported the compression changes, and the energy disperses once more into the surrounding field. The wave relaxes back into the broader pattern, its height diminishing as the surface returns to a more even distribution. This tendency for energy to gather and release reveals a subtle aspect of the ocean's behavior. It is not a system where motion spreads uniformly at all times, but one where local conditions can create pockets of intensity. These pockets emerge from the same principles that govern the rest of the surface, yet they produce outcomes that stand apart, shaped by the way energy can, for a brief moment, find itself drawn into a single, focused expression. Far from the surface where waves are visible, large bodies of water move with a steady persistence, flowing across the ocean as currents that carry heat, salt, and momentum over vast distances. These currents are not shaped by wind alone. They arise from differences in temperature, density, and the rotation of the Earth, forming pathways that remain stable even as the surface above them changes from moment to moment. Their presence is subtle when viewed from above, yet they exert a quiet influence on everything that passes over them. When waves travel across these moving bodies of water, their behavior begins to shift. A wave moving in the same direction as a current may stretch, its energy spreading over a longer distance, its crest becoming less steep. In contrast, a wave moving against a current encounters resistance, as the forward motion of the water beneath it opposes its own progression. This interaction compresses the wave, shortening its wavelength and increasing its height. The energy remains, but it is forced into a smaller space, altering the shape of the surface in a way that becomes more pronounced, with stronger opposition. This effect becomes particularly noticeable in regions where powerful currents meet incoming wave systems from distant storms. The Agulhas Current, flowing along the southeastern coast of Africa, provides a well-studied example. It moves swiftly southward, carrying warm water in a narrow, concentrated stream. When waves generated in the Southern Ocean travel northward into this current, the opposing directions create conditions where compression intensifies. The surface becomes more irregular, with steeper crests and deeper troughs forming over relatively short distances. Within these interactions, the potential for extreme elevations increases. The opposing motion does not create energy on its own, but it redistributes what is already present, focusing it into sharper, more confined forms. Waves that might otherwise pass with moderate height can grow significantly as they encounter the current, their profiles changing in response to the altered flow beneath them. The alignment of wave direction and current strength determines the extent of this amplification, creating localized zones where the surface behaves differently from surrounding areas. These zones are not fixed in place, yet they recur in regions where currents and wave pathways consistently intersect. Along the Agulhas region, as well as parts of the North Sea and sections of the Indian Ocean, similar conditions have been observed. The presence of strong currents combined with incoming wave systems establishes an environment where the usual distribution of wave heights can shift, allowing for more pronounced variations within a relatively confined space. The interaction between waves and currents also affects the timing of wave groups. As waves slow down against a current, they begin to cluster more closely together, increasing the likelihood of interactions that can further amplify individual crests. This clustering does not guarantee the formation of a single dominant wave, but it raises the potential for energy to gather in ways that depart from the broader pattern. In this layered movement, where surface motion meets deeper flow, the ocean reveals another dimension of complexity. The visible waves carry the imprint of forces that extend far below, shaped by currents that move independently of the wind above. When these layers align in opposition, the surface responds by tightening, steepening, and, at times, producing elevations that stand out within their immediate surroundings, formed through the quiet but persistent influence of water moving beneath water. Wind leaves its signature across the sea in ways that are both visible and measurable, shaping the surface through sustained contact over distance and time. The resulting waves carry a memory of that interaction, their size and spacing reflecting how long the wind has acted and how consistently it has flowed. In strong conditions, these waves grow larger, their crests lifting higher and their faces becoming steeper, yet they remain part of a continuous field, rising through accumulation rather than sudden change. Within storms, this process becomes more pronounced. Waves build gradually as energy is transferred from the atmosphere into the water, each passing moment adding to the motion already present. The surface evolves in a steady progression where larger waves emerge among smaller ones, forming groups that follow a recognizable pattern. Even at their most intense, these waves retain a connection to the system that produced them, their growth tied to the persistence of the wind and the extent of the open water it crosses. A rogue wave does not follow this pathway. It appears within conditions that may already include large waves. Yet its presence cannot be explained by wind strength alone. The surrounding sea may reflect the influence of a storm, but the rogue wave exceeds what that influence would normally produce. Its height does not emerge through the same gradual buildup, nor does it belong to the sequence of waves that define the broader field. The distinction lies in how energy is organized. Storm waves represent a distribution shaped by sustained forcing, where the largest waves are still part of a continuum that can be anticipated within statistical limits. Their peaks rise higher than average, but they do so within a structure that maintains proportional relationships between size and frequency. The system remains coherent, even as it becomes more energetic. In contrast, a rogue wave reflects a moment where that coherence is interrupted. The energy present in the surrounding sea does not increase overall, but it becomes concentrated in a way that produces a single, disproportionate elevation. This concentration occurs over a short time scale, without the extended buildup associated with wind-driven growth. The result is a crest that stands apart from its neighbors, not as the natural extension of the storm's intensity, but as a deviation from it. This difference can be understood in terms of timing and distribution. Wind-driven waves evolve over minutes to hours, their characteristics changing gradually as conditions persist. Rogue waves emerge within seconds, their formation linked to interactions that momentarily align to amplify height. The underlying energy is already present in the system, but it is rearranged rather than increased, gathered into a form that exceeds the surrounding pattern. Observations of such events often occur during rough seas, which can lead to the impression that they are simply the largest expressions of storm activity. Yet careful analysis shows that their properties differ in important ways. Their steepness, isolation, and rapid formation distinguish them from the broader population of waves generated by wind. They are not the culmination of the storm's growth, but an interruption within it. In this way, the ocean reveals a layered behavior. Wind shapes the general state of the surface, establishing the conditions within which waves move and interact. Within those conditions, additional processes can act, redistributing energy in ways that produce outcomes beyond what the wind alone would suggest. The surface becomes a place where gradual forces and sudden rearrangements coexist, each contributing to the forms that appear and then pass back into the larger motion. Beneath the shifting surface lies a kind of order that does not repeat in simple cycles, yet still follows rules that shape how motion unfolds. The ocean behaves as a chaotic system, where patterns exist without settling into exact repetition, and where small differences in starting conditions can lead to outcomes that diverge over time. What appears irregular is not without structure, but the structure is sensitive, changing as interactions evolve across scales, both large and small. In such systems, predictability has limits that emerge not from randomness, but from complexity. Each wave is influenced by many factors at once, including direction, speed, phase, and the presence of other waves moving nearby. These influences combine continuously, forming a network of interactions that cannot be reduced to a single cause or pathway. Even slight variations in one part of this network can alter how energy moves through the rest, creating differences that grow as time passes. A small shift in alignment between waves, barely noticeable at first, can change how their energies combine. A difference in timing, measured in fractions of a second, can determine whether crests reinforce each other or pass without effect. Over short distances, these variations remain subtle, blending into the broader motion. Over longer distances and durations, they can accumulate, leading to outcomes that diverge from what might have been expected based on initial observations. This sensitivity means that precise prediction becomes increasingly difficult as the system evolves. Models can describe general behavior, outlining the range within which most waves will fall, but they cannot track every interaction in detail. The number of variables involved grows rapidly, and the information required to define the system completely exceeds what can be measured in practice. As a result, forecasts rely on probabilities, offering likely conditions rather than exact outcomes. Within this framework, extreme events emerge not as isolated anomalies, but as part of the system's natural variability. They arise when a sequence of interactions aligns in a way that amplifies energy beyond the typical range. The conditions that produce them may begin with ordinary differences, yet through a chain of influences, those differences become significant. The process is continuous, with no clear boundary separating common behavior from rare outcomes. The ocean's surface reflects this interplay between order and unpredictability. Patterns can be recognized, and tendencies can be described, yet each moment carries a degree of uncertainty shaped by the system's sensitivity. Two regions with similar conditions may evolve differently over time, not because the underlying principles have changed, but because the initial details were not identical. The divergence grows quietly, embedded within the ongoing motion. This perspective alters how the sea is understood. Rather than a system that can be fully anticipated given enough information, it becomes one where understanding is framed in terms of likelihood and range. The limits of prediction are not failures of observation, but inherent features of the system itself. Even with improved measurements and more refined models, there remains a horizon beyond which exact outcomes cannot be determined. In this way, the ocean holds patterns that are both structured and fluid, shaped by interactions that are consistent in principle, yet variable in expression. Its behavior unfolds within a space where small changes can lead to significant differences, and where the path from one moment to the next carries possibilities that extend beyond precise foresight. Grounded instead in the quiet complexity of a system that is always in motion, a crest can take many forms as it moves across the sea, some broad and gently curved, others narrow and sharply defined. Among these variations, the shape associated with a rogue wave carries a distinct geometry, one that reflects the concentration of energy within a limited space. It rises with a steepness that contrasts with the surrounding surface, its profile appearing compressed, as though the usual spacing between waves has been drawn inward. The face of such a wave often approaches a near vertical angle. Instead of a gradual slope leading up to the crest, the water lifts abruptly, forming a wall-like surface that ascends over a short horizontal distance. This steepness is not merely a visual impression, but a direct result of how energy is distributed within the wave. When energy becomes concentrated, the wavelength shortens, bringing the crest and trough closer together. The wave does not extend outward in a long, rolling form, but gathers upward, increasing its height while reducing its length. This shortened wavelength contributes to the sharpness of the crest, Rather than forming a rounded peak, the top of the wave becomes more pointed, its curvature tightening as the water is forced into a smaller area. The transition from the rising face to the descending side becomes more abrupt, creating a profile that stands apart from the smoother shapes commonly seen under stable conditions. The wave appears more compact, its structure defined by intensity rather than breadth. As the crest sharpens, the stability of the wave changes. In more typical conditions, waves can travel long distances while maintaining their form, their energy balanced between forward motion and vertical displacement. In the case of a rogue wave, the concentrated energy disrupts this balance. The steep face and sharp crest place the wave closer to a breaking point, where the water can no longer support its own structure. When breaking occurs, it often does so with a different character than that of more familiar waves. Instead of spilling forward gradually, the crest can collapse with a sudden release, sending water downward and outward with considerable force. The motion is less like a rolling progression and more like a rapid overturning, where the upper portion of the wave loses support and falls into the trough below. This behavior is linked to the wave's steepness, as the angle of the face determines how the crest interacts with gravity and momentum. The breaking process also reflects the limited space over which the wave has formed. Because the wavelength is short, the energy does not have room to dissipate gradually. When the structure gives way, the release is concentrated, producing a localized impact that differs from the more distributed breaking seen in longer waves. The surrounding surface, which may still follow a broader pattern, provides little transition into this event, emphasizing the contrast between the rogue wave and its environment. This distinct shape is not a permanent feature of the ocean, but a momentary expression of conditions that have aligned to produce it. As the wave forms, reaches its peak, and then breaks or disperses, its structure reflects the underlying processes that brought energy into focus. The steep face, the shortened wavelength, and the sharp crest are all manifestations of that concentration, shaping a form that exists briefly before returning to the broader continuity of the sea. Contact between a moving wall of water and a solid surface unfolds in a span so brief that it resists gradual description. The approach carries momentum gathered over distance, concentrated into a narrow region where the wave's mass and velocity meet the structure directly. At that point, motion does not ease into contact. It transfers abruptly, converting the wave's energy into force against the surface it encounters. Water, though fluid, becomes effectively dense when driven at speed. The leading face of a steep wave presents a volume that behaves with weight and inertia, pressing forward with a force that depends on both its height and the speed at which it moves. When this mass reaches a ship's hull, the interaction is governed by pressure, the force applied over a given area. In ordinary conditions, hulls are designed to withstand distributed loads, where water pushes and recedes in a pattern that allows stresses to spread and dissipate. In the case of an extreme wave, that distribution changes. The impact can occur over a limited section of the hull, concentrating force into a smaller area. The pressure rises sharply, exceeding the levels anticipated under typical sea states. Structural elements that are intended to flex slightly under load may instead experience stresses that approach or surpass their design limits. The material responds according to its properties, bending, cracking, or, in some cases, failing outright. The timing of this interaction contributes to its severity. Because the wave's face is steep and its approach rapid, the duration of peak pressure is short. The hull does not have time to adjust gradually. Instead, It encounters a sudden load that reaches its maximum almost immediately. This rapid onset reduces the ability of the structure to distribute stress internally, increasing the likelihood of localized damage. Windows and superstructures positioned above the main hull are particularly exposed. These elements are often designed for conditions where water reaches them through spray or moderate wave action, not through direct, high-pressure contact. When a large wave rises high enough to meet these areas, the force can exceed their tolerance. Glass can fracture, frames can deform, and water can enter spaces not intended to be exposed to such loads. The direction of impact also plays a role. A wave striking the side of a vessel exerts pressure differently than one encountered head-on. Side impacts can produce bending forces along the length of the hull, while head-on impacts concentrate force toward the bow. Each orientation introduces stresses that the structure must absorb, and in extreme conditions, these stresses can combine in ways that challenge the vessel's integrity. Energy transfer during impact is not limited to the initial contact. As the wave passes, water continues to move around and over the structure, applying additional forces that can compound the effect. The sequence unfolds quickly, with little separation between the initial strike and the subsequent flow. The cumulative result is a brief but intense period where the vessel experiences forces beyond those encountered in more typical conditions. Damage occurs within this narrow window. Materials respond according to their limits, and when those limits are exceeded, changes happen immediately. There is no gradual progression from intact to compromised. The transition is abrupt, reflecting the nature of the forces involved. Once the wave has passed, the surface returns to its broader motion, but the effects of the interaction remain, shaped by the moment when energy concentrated into contact and transferred its force in a single, decisive interval. Every vessel carries within its structure an assumption about the sea it will encounter. That assumption is not arbitrary. It is drawn from decades of observation, from records that describe how waves typically behave, how often certain heights occur, and how forces distribute across a hull under ordinary conditions. Design standards translate these patterns into limits, defining the loads a ship is expected to withstand while maintaining integrity and stability. Hull geometry reflects these expectations. The curvature of the bow, the thickness of plating, and the arrangement of internal supports are all shaped by a balance between strength and efficiency. Ships are built to endure repeated impacts from waves that follow predictable distributions, where the largest forces are rare but still fall within a defined range. Within this range, materials can flex slightly, absorbing energy and returning to form without permanent damage. This approach works effectively for the vast majority of conditions encountered at sea. The structure disperses stress along its length, allowing forces to spread rather than concentrate. Reinforcements are placed where loads are expected to be highest, and design calculations account for the cumulative effect of many impacts over time. The result is a system that performs reliably when the ocean behaves within its established patterns. Vulnerability emerges when those patterns are exceeded in ways the design does not anticipate. A wave that rises significantly above the expected range introduces forces that are not evenly distributed. Instead of spreading across a broad area, the load may focus on a specific section of the hull. This concentration can create stresses that surpass the material's capacity, leading to deformation or fracture. Windows and upper structures illustrate this limitation clearly. These elements are positioned above the main hull and are often designed for exposure to spray, wind, and moderate wave contact. Their materials and supports reflect these conditions, balancing visibility and weight with structural requirements. When a wave reaches higher than anticipated and strikes these areas directly, the pressure can exceed their tolerance. Glass can fail under sudden load, and once breached, water can enter spaces not intended to withstand such intrusion. The interaction between structure and force is further complicated by the orientation of the vessel at the moment of impact. A ship may be pitched or rolled by surrounding waves, altering how it meets an incoming crest. This change in angle can expose surfaces that would otherwise remain above the waterline, or it can shift the distribution of stress along the hull. The structure, designed for a range of orientations, may encounter a combination that concentrates force in unexpected ways. Modern records provide examples of how these interactions unfold. Large container ships have reported sections of their bow plating bending inward after encountering unusually steep waves. In some cases, windows on the bridge have shattered, allowing water to enter control areas. Cruise vessels have experienced localized damage to upper decks, where the height of the wave exceeded the level those structures were designed to face. These events do not occur frequently, but they reveal how deviations from expected conditions can challenge even well-engineered designs. The materials themselves play a role in how damage develops. Steel, commonly used in hull construction, has strength and flexibility within certain limits. When stresses exceed those limits, the material does not gradually adjust. It yields or fractures, creating changes that can propagate if the load continues. The transition from intact structure to damaged section can happen within a single impact, reflecting the intensity of the forces involved. In this way, the vulnerability of ships is not a result of weakness, but of alignment between design and expectation. Vessels are built to match the patterns most commonly observed, and within those patterns, they perform as intended. When the ocean produces conditions that fall outside those expectations, the structure encounters forces it was not specifically shaped to endure, revealing the boundary between typical performance and the extremes that occasionally arise. Logbooks preserve moments in a restrained language, lines written after the motion has passed, when there is time to record what was seen and what changed. Among routine entries of course and weather, there are occasional descriptions that depart from the usual rhythm, brief accounts that note a single event standing apart from surrounding conditions. These entries do not linger on interpretation. They mark time, position, and the presence of a wave that did not resemble the others. In one such account, a cargo vessel traveling through open water recorded a sudden rise ahead of the bow, described not as part of the existing sequence, but as a solitary elevation. The surrounding sea was active yet consistent, with waves following a regular spacing. Then, within that pattern, a larger form appeared, lifting sharply and passing beneath the ship before the surface returned to its previous state. The entry notes a strong impact and a momentary loss of forward motion, followed by a continuation of the voyage under unchanged conditions. Similar reports appear across different oceans and decades, often separated by distance, yet aligned in structure. Crews describe a single wave rising without gradual buildup, its height exceeding the surrounding surface by a noticeable margin. The event unfolds quickly, leaving little time for response. Instruments may register a sudden change in motion or pressure, but the duration is brief, and by the time adjustments are made, the wave has already passed. These encounters are not always accompanied by severe damage, though some include records of structural strain or equipment failure. In certain cases, ships have reported broken windows, bent railings, or localized deformation along the hull. The descriptions remain concise, focusing on what was observed rather than attempting to explain its cause. The emphasis is on the contrast between the event and the conditions immediately before and after it. The transient nature of these waves is a consistent feature in such accounts. Crews often note that the sea returned to its prior pattern within moments, as if the event had been contained within a narrow interval. There is no extended sequence of unusually large waves, no gradual escalation that would signal a change in conditions. The encounter exists as a single deviation, recorded between entries that describe a more typical surface. In some reports, the timing of the event is marked with precision, allowing it to be correlated with instrument data or satellite observations. These correlations provide additional confirmation, linking subjective descriptions with measured changes in wave height or vessel motion. Even when such data is available, the written accounts retain their directness, conveying the experience in terms that reflect the immediacy of the moment. The language used by crews tends to be practical, shaped by the need to communicate clearly within the context of navigation and safety. Phrases such as sudden rise, steep face, or single large wave appear across different records, suggesting a shared attempt to describe a form that does not fit easily within standard categories. The consistency of these descriptions, despite variations in location and vessel type, adds to their significance. Across these accounts, a pattern emerges that aligns with measured observations while retaining the perspective of those who encountered the events directly. The waves appear without extended warning, interact with the vessel over a short interval, and then pass, leaving the surrounding sea to continue its motion as before. The records do not present a continuous series of extremes, but isolated moments that stand apart within otherwise ordinary conditions. Through these entries, the open ocean reveals instances where its behavior diverges briefly from expectation, captured in writing that reflects both the precision of observation and the brevity of the experience itself. Light defines distance on the ocean, giving form to motion that would otherwise blend into a continuous surface. During the day, variations in height and spacing can be seen as they approach, allowing the eye to follow the rhythm of the water and anticipate changes within it. The horizon provides reference, and the movement of crests can be traced over time, offering a sense of how the surface is evolving. At night, this visual structure recedes. The boundary between water and sky becomes less distinct, and the surface loses the contrast that reveals its shape. Waves remain present in full detail, yet their outlines are no longer easily perceived at a distance. What can be seen is limited to what falls within the reach of available light, often confined to the immediate area around a vessel. Beyond that, motion continues unseen, advancing without visual indication. This reduction in visibility alters how encounters unfold. Without the ability to observe approaching forms clearly, the time available to recognize and respond to changes in the surface becomes shorter. A wave that might be noticed earlier in daylight can remain undetected until it is much closer, reducing the interval between awareness and impact. The sequence of events compresses, not because the wave moves faster, but because perception begins later. Artificial lighting provides only partial compensation. Deck lights illuminate nearby water, revealing texture and movement within a limited range, but they do not extend far enough to capture larger patterns developing at a distance. The illuminated area can create a sense of clarity within its boundary, while beyond it, the surface remains indistinct. This contrast can make distant changes more difficult to perceive as the eye adjusts to the brightness of the immediate surroundings. Instrumentation continues to operate regardless of light conditions, measuring motion and providing data that reflects the state of the sea. However, The translation of that data into immediate understanding requires interpretation. Sudden changes in readings can indicate an approaching variation, yet they do not present a visual form that can be tracked in the same way as a visible crest. The connection between measurement and perception becomes less direct. In this environment, many encounters are first recognized through the effects they produce rather than through visual observation. A shift in the vessel's motion, a change in pitch or roll, or the sound of water impacting the structure can signal the presence of a larger wave. By the time these cues are registered, the event is already underway, and the opportunity for adjustment has largely passed. Reports from nighttime conditions often reflect this sequence. Crews describe a sudden change without prior visual indication, followed by the immediate passage of the wave and a return to the previous state. The absence of clear sightlines contributes to the impression that the event appeared without warning, even though it followed the same physical processes as those observed in daylight. The role of visibility, then, is not to alter the formation of waves, but to shape how they are experienced. In reduced light, the ocean's surface becomes less legible, its patterns harder to interpret at a distance. The timing of perception shifts closer to the moment of contact, narrowing the space between observation and interaction. Within this narrower interval, the sea continues its motion, carrying forms that may remain unseen until they reach the point where their presence is no longer defined by sight, but by the direct interaction with the vessel itself. Far above the surface, where the curvature of the earth becomes visible and weather systems unfold as slow-moving shapes, satellites pass in steady orbits, scanning the oceans with instruments that measure height and motion from a distance. These observations do not rely on proximity or fixed position. They move continuously, crossing vast areas and returning at regular intervals, building a record that extends across regions too large to be captured by ships or stationary sensors alone. The method is precise in its simplicity. Radar altimeters send signals toward the ocean and measure the time it takes for those signals to return. From this, the distance between the satellite and the sea surface can be calculated with remarkable accuracy. As the satellite travels, it traces a line across the water, recording variations in height along its path. Each pass adds another segment to a growing map, where the surface is represented not as a single image, but as a collection of measured profiles. When these profiles are assembled over time, patterns begin to emerge that extend beyond local observations. Areas that once appeared uniform reveal subtle variations, and events that would have gone unnoticed at sea become visible within the data. Among these events are isolated peaks that rise sharply above their surroundings, matching the characteristics associated with rogue waves. Unlike earlier reports, these measurements do not depend on interpretation. They exist as recorded deviations within a consistent system of observation. As more data accumulated, the frequency of such events became clearer. What had been considered exceedingly rare began to appear with greater regularity across different regions. The measurements did not suggest that every part of the ocean produced these waves equally, but they showed that the conditions allowing for their formation were more widespread than previously assumed. The ocean, viewed from this vantage point, revealed a distribution of extremes embedded within its broader behavior. Certain regions displayed higher concentrations of these recorded peaks. Areas influenced by strong currents, complex wave interactions, or consistent storm activity showed patterns where elevated waves occurred more often. The data did not isolate a single cause, but it highlighted correlations between environmental conditions and the likelihood of encountering such events. These correlations provided a broader context, linking individual measurements to the dynamics of larger systems. The global perspective offered by satellites also changed how continuity was understood. Instead of isolated incidents reported by individual vessels, rogue waves could be placed within a network of observations that spanned oceans. A measurement in one region could be compared with another thousands of kilometers away, revealing similarities in structure and behavior. The ocean's variability became visible on a scale that connected local events to global patterns. This shift in observation did not eliminate uncertainty, but it refined the boundaries within which it existed. The presence of these waves was no longer confined to anecdote or rare measurement. It became part of a documented record, supported by repeated observation across different conditions. The data suggested that, while such waves remain uncommon relative to the total number of waves at sea, they are not as infrequent as earlier models had implied. Through this broader lens, the ocean appears as a system where extremes are distributed across space and time, shaped by the same underlying processes that govern more typical conditions. The satellites do not alter the surface they observe, but they extend the ability to perceive it, revealing patterns that were always present yet previously unseen, embedded within the continuous motion of water across the planet. Over time, as observations accumulated from different sources and across wider regions, a gradual adjustment began to take shape in how these waves were understood. What had once been treated as exceedingly rare, positioned at the far edge of probability, began to appear with a frequency that did not align with earlier expectations. The change did not arrive suddenly, but through the steady addition of measurements, each one contributing to a broader picture that extended beyond initial assumptions. The revised estimates emerged from a combination of satellite records, fixed platform data, and instrumented vessels, all capturing moments where wave heights exceeded the surrounding field by a significant margin. When these observations were examined collectively, they revealed that such events were not confined to isolated occurrences separated by vast spans of time. Instead, they appeared across different oceans and under varying conditions, suggesting a level of regularity within the system's variability. Earlier models had relied heavily on statistical distributions derived from limited datasets. These models described the likelihood of wave heights based on observed patterns, extending those patterns to estimate the occurrence of more extreme values. In doing so, they assumed that the processes governing typical waves would continue to apply at larger scales, with probabilities decreasing smoothly as height increased. This approach captured much of the ocean's behavior accurately, but it did not fully account for mechanisms that could concentrate energy more efficiently in localized regions. As understanding expanded to include nonlinear interactions, wave focusing, and the influence of currents, it became clear that the pathways leading to extreme waves were more accessible than previously thought. The system did not require exceptionally rare conditions to produce such events. Instead, it could generate them through combinations of factors that, while individually common, aligned in ways that amplified their effects. This realization shifted the perception of rarity, moving it from near impossibility to low but meaningful probability. The implications of this shift extend beyond theoretical understanding. Ocean travel, which depends on assessments of risk and reliability, is influenced by how often extreme conditions are expected to occur. Design standards, routing decisions, and operational practices are all informed by statistical models of the sea. When those models underestimate certain types of events, the resulting expectations may not fully reflect the range of conditions that vessels can encounter. In response, Adjustments have been made to incorporate broader data sets and more complex modeling approaches. These refinements aim to capture a wider spectrum of behavior, acknowledging that extremes are part of the system rather than distant outliers. The goal is not to predict the exact moment of occurrence, but to better represent the likelihood and potential impact of such events within planning and design frameworks. Despite these advances, the ocean retains a degree of unpredictability that cannot be fully resolved. Revised estimates provide a clearer sense of frequency, yet they remain probabilistic, describing tendencies rather than certainties. For those navigating open water, this means that while the understanding of risk has improved, it remains defined by a range of possibilities shaped by the system's complexity. Within this evolving perspective, the presence of these waves becomes part of the broader character of the sea. They are not anomalies set apart from normal behavior, but expressions of processes that operate continuously beneath the surface. Their occurrence, more frequent than once believed, reflects the ocean's capacity to produce variation within its patterns, revealing a landscape where extremes are woven quietly into the fabric of its motion. At the edge of what has been measured and modeled, understanding settles into a space that is neither fixed nor finished. The ocean has revealed many of its governing principles, and the processes that shape wave behavior are now described with increasing clarity. Energy transfer, wave interaction, and the influence of currents are no longer abstract ideas, but elements that can be observed, simulated, and compared across different conditions. Yet, within this growing framework, there remain aspects that do not resolve into complete explanation. Current models capture much of the ocean's typical behavior with remarkable accuracy. They describe how waves form, how they travel, and how they interact over time. Nonlinear dynamics, once only partially considered, are now integrated into simulations that allow for more realistic representations of the surface. These models can reproduce conditions where energy concentrates, producing peaks that resemble those observed in nature. In controlled environments and computational studies, the mechanisms that lead to extreme waves can be traced, offering insight into how such events emerge from ordinary interactions. Despite this progress, the translation from model to prediction remains limited. The ocean is not a closed system with fixed inputs. It is influenced by variables that change continuously, including wind patterns, current strength, and the evolving state of the surface itself. Each of these factors interacts with the others, creating a web of conditions that cannot be fully captured at every point in space and time. The models rely on approximations, representing the system at a scale that balances detail with computational feasibility. This balance introduces uncertainty. While the general pathways leading to extreme waves are understood, the precise conditions that bring them into existence at a specific moment remain difficult to isolate. Small differences in initial conditions, already known to influence outcomes in complex systems, can alter how energy is distributed across the surface. These differences may not be measurable with sufficient resolution, leaving gaps between what is observed and what can be predicted. Field measurements continue to expand the available data, yet they also reveal the limits of observation. Instruments provide detailed records at specific locations, and satellites offer broader coverage, but the ocean's vastness means that many interactions occur beyond direct measurement. The surface evolves continuously, and even with dense observation networks, there are intervals and regions where the exact state of the system is inferred rather than directly known. Research efforts are moving toward integrating multiple sources of data with increasingly sophisticated models. Advances in computational power allow simulations to include more variables and finer resolution, capturing interactions that were previously simplified. Machine learning techniques are being explored to identify patterns within large datasets, seeking relationships that may not be evident through traditional analysis. These approaches aim to bridge the gap between observation and prediction, improving the ability to anticipate conditions that favor the formation of extreme waves. At the same time, experimental studies in controlled environments continue to refine understanding of wave dynamics. Wave tanks and laboratory setups allow specific conditions to be recreated and examined in detail, isolating factors that contribute to energy concentration. These studies provide clarity on individual processes, which can then be incorporated into broader models that represent the open ocean. Even as these efforts advance, the system retains a level of complexity that resists complete resolution. The ocean's behavior emerges from interactions that span scales from small ripples to large currents, each influencing the others in ways that are consistent in principle but variable in outcome. The physics that describe these interactions are known, yet their combined expression remains only partially predictable. Within this space of partial understanding, the ocean continues to be studied as both a system that can be described and one that cannot be fully anticipated. The knowledge that exists provides a framework, while the uncertainties define the boundaries of that framework, marking where observation and explanation continue to move forward together. Prediction begins with observation, yet the ocean offers its details unevenly, revealing some patterns clearly while keeping others dispersed across distance and time. Forecasting systems draw from this uneven field, combining measurements of wind, currents, and existing wave conditions to describe how the surface is likely to evolve. These systems perform well in outlining general states, indicating regions of higher activity or calmer conditions, and estimating the range within which most waves will fall. Within this framework, the limits of prediction become evident when attention turns to individual extremes. The models describe averages and distributions, not specific peaks. They can indicate when conditions are favorable for larger waves, but they do not resolve the exact alignment of interactions that produces a single, sharply elevated crest. The resolution required to capture such alignment would demand knowledge of the system at a level of detail that is not continuously available. Forecasts rely on grids that divide the ocean into segments, each representing conditions over a defined area. Within each segment, variables are averaged, smoothing out smaller variations to make computation manageable. This approach allows the system to operate across vast regions, but it also means that localized interactions, those that occur within a narrow space and brief interval, may not be fully represented. The formation of a rogue wave depends on precisely such interactions, making them difficult to isolate within the broader model. Even with improved computational methods, uncertainty remains tied to the initial state of the system. Small inaccuracies in measurement or gaps in data can propagate through the model, influencing how energy is distributed over time. These differences may be minor in the context of general forecasting, yet they become significant when considering events that arise from fine-scale alignments. The sensitivity of the system amplifies these small uncertainties, limiting the precision of prediction. Efforts toward early warning focus on identifying conditions that increase the likelihood of extreme waves. By analyzing combinations of wave direction, current strength, and energy distribution, researchers can highlight regions where the potential for such events is elevated. These assessments do not predict a specific wave, but they provide context, indicating when and where caution may be warranted based on the underlying dynamics. Advances in observation contribute to this approach. Satellite data, buoy networks, and ship-based measurements offer a more detailed view of the ocean's state, allowing models to incorporate a wider range of information. Real-time data feeds improve the representation of current conditions, reducing some of the uncertainty associated with initial inputs. As these systems evolve, they move closer to capturing the complexity of the surface, though they do not eliminate the inherent variability. Experimental forecasting techniques explore the possibility of detecting precursor patterns, subtle changes in the wave field that might precede the formation of an extreme event. These patterns are difficult to distinguish from normal variability, and their identification remains an area of active study. The challenge lies in separating meaningful signals from the constant fluctuations that characterize the ocean. Despite these efforts, prediction remains bounded by the nature of the system itself. The ocean's behavior emerges from interactions that are both structured and sensitive, where small differences can lead to divergent outcomes. Models can outline the conditions under which extremes are more likely, but they cannot determine the exact moment when those conditions will produce a specific event. In this way, forecasting provides a framework of possibility rather than certainty. It describes the range within which the ocean is likely to move, while acknowledging that within that range there exist moments that arise beyond precise anticipation, shaped by the same processes that define the surface as a whole. Across the global ocean, conditions are not evenly distributed. There are regions where motion gathers complexity more readily, where currents, wind systems, and incoming wave fields intersect in ways that create a higher likelihood of unusual surface behavior. These areas are not defined by a single feature, but by the way multiple influences converge, shaping environments that differ subtly yet significantly from surrounding waters. In the South Atlantic, long wave trains generated by distant storms travel across open expanses, carrying energy that remains organized over great distances. As these waves move into regions where currents shift direction or intensity, their structure begins to change. The meeting of opposing flows can compress waveforms, shortening their length and increasing their height. Within these interactions, the surface becomes less uniform, and the distribution of wave energy begins to favor sharper variations. The North Sea presents a different configuration, shaped by its semi-enclosed geography and the influence of persistent weather systems. Strong winds pass frequently across its relatively shallow waters, generating waves that interact with both currents and the seafloor. The limited depth modifies how waves travel, encouraging steeper profiles and more complex patterns of interference. Fixed structures in this region have provided detailed measurements, revealing instances where individual waves rise significantly above the surrounding field under conditions that might otherwise appear typical. Further east, parts of the Indian Ocean exhibit similar tendencies, particularly along routes where major currents flow against prevailing wave directions. These currents, driven by large-scale circulation patterns, create zones where the movement of water beneath the surface alters the behavior of waves passing above. When combined with seasonal wind systems, the result is a dynamic environment where energy can be redistributed unevenly, allowing localized amplifications to occur more readily. The role of weather systems extends beyond generating waves. Storms influence both the direction and consistency of wave fields, sending multiple wave trains across the same region from different origins. When these trains intersect, the potential for complex interactions increases. The presence of currents adds another layer, modifying how these interactions unfold. The combined effect is a surface where the usual patterns become more intricate and where the likelihood of concentrated energy rises. Shipping routes that pass through these regions encounter conditions shaped by this interplay. The routes themselves are often determined by efficiency and distance, following paths that align with major trade corridors. In doing so, they intersect with areas where the underlying dynamics favor variability. The increased risk is not constant, but it is elevated relative to regions where such interactions are less pronounced. This variation does not imply that every passage through these areas will involve extreme waves. Most of the time, the surface remains within expected limits, and vessels move through without encountering unusual conditions. The distinction lies in probability, where the combination of currents, wave directions, and weather patterns creates a higher chance of deviations from the norm. Understanding these regions involves recognizing how multiple factors align over space and time. The ocean's behavior is shaped by layers of influence, each contributing to the overall state of the surface. Where these layers intersect in particular ways, the potential for concentrated energy increases, forming zones where the patterns observed elsewhere may shift toward greater variability. In this global perspective, the ocean reveals areas where its dynamics are more tightly woven, where the interactions between forces create conditions that differ in subtle but meaningful ways. These regions, shaped by currents and weather systems, mark places where the surface carries a higher likelihood of producing forms that stand apart from the broader continuity of the sea. Anchored deep into the seafloor, offshore platforms remain in place while the ocean moves around them, creating a point of reference that does not shift with the surface. This fixed position changes how waves are observed. Instead of being carried along by the motion, as a ship would be, the structure experiences each passing wave relative to a stable frame, allowing measurements to reflect the full height and form of the water as it rises and falls. Instruments mounted on these platforms operate continuously, recording surface elevation, pressure, and motion without interruption. Because the platform does not travel, the data it collects represents a consistent location over time, capturing variations that might otherwise be missed by moving observers. This continuity provides a detailed record of how the surface behaves under different conditions, including moments when individual waves exceed the surrounding pattern. The reliability of these measurements comes from both stability and repetition. Each wave is recorded in the same way, using sensors that are calibrated and fixed in position. There is no need to account for changes in speed or direction, and no reliance on human interpretation at the moment of observation. The result is a dataset that reflects the ocean's motion with a level of consistency that allows subtle deviations to be identified and examined. When extreme waves pass through these locations, the interaction with the structure is recorded in detail. The height of the wave, its shape, and the forces it exerts can be measured directly. In some cases, these measurements have been accompanied by reports of physical impact, where parts of the platform experience loads beyond their typical range. Structural components may show signs of strain, and equipment positioned above the expected waterline can be exposed to direct contact. Damage reports from offshore platforms provide insight into how these forces manifest. Instances of bent railings, damaged sensors, or deformed structural elements have been documented following encounters with unusually large waves. These effects are often localized, reflecting the concentrated nature of the impact. The structure as a whole remains intact, but specific areas reveal how the force was applied and where it exceeded design expectations. The lessons drawn from these observations extend into both engineering and understanding of ocean behavior. From an engineering perspective, The data informs adjustments to design standards, encouraging consideration of conditions that fall outside earlier statistical assumptions. Components may be reinforced, and critical systems positioned to reduce exposure to unexpected loads. The goal is not to eliminate all risk, but to align design more closely with the range of conditions that can occur. From a scientific perspective, the measurements contribute to a more complete picture of wave dynamics. The ability to capture extreme events with precision allows researchers to compare observations with theoretical models, identifying where those models align with reality and where they require refinement. Each recorded event adds to a growing body of evidence that shapes how the ocean is described and understood. The presence of fixed structures thus serves a dual role. They operate as working platforms within the ocean, and at the same time as points of observation that reveal aspects of the surface that might otherwise remain unmeasured. Through their stability, they provide clarity, allowing the motion of the sea to be recorded against a constant reference. In this steady relationship between structure and movement, the ocean's variability becomes more visible. Waves pass, measurements accumulate, and within that record, moments of deviation are preserved, offering insight into how the surface behaves not only under typical conditions, but also in those brief intervals when it exceeds them. Two very different kinds of ocean motion can produce a sudden rise of water, yet their origins and behavior follow separate paths beneath the surface. One begins deep within the earth, where tectonic movement displaces large volumes of water almost instantly. The other forms entirely at the surface, shaped by interactions between waves, currents, and the shifting patterns already present. Though both can produce elevated water levels, the processes that create them do not overlap. A tsunami originates when the seafloor itself moves, often during an undersea earthquake, landslide, or volcanic event. This displacement pushes water upward across a wide area, setting in motion a wave that carries energy through the entire depth of the ocean. Unlike surface waves, which are driven by wind and confined largely to the upper layers, a tsunami involves the full column of water from surface to seabed. This difference defines how it travels and how it appears. In deep water, a tsunami has a very long wavelength, sometimes extending hundreds of kilometers from one crest to the next. Its height in the open ocean may be relatively small, making it difficult to detect without instruments, yet its speed can be considerable, moving across the basin at rates comparable to a fast aircraft. The energy is spread over a vast distance, and the wave does not present as a steep, localized peak while far from land. As a tsunami approaches shallower regions, its behavior changes. The reduction in depth slows the wave, compressing its wavelength and increasing its height. The water rises more noticeably, often forming a broad surge rather than a sharply defined crest. The transformation is gradual, shaped by the interaction between the moving wave and the seafloor, and it unfolds over a larger spatial scale than surface waves typically exhibit. A rogue wave, by contrast, is generated within the existing surface conditions of the ocean. It does not involve displacement of the seafloor or the full depth of the water column. Instead, it emerges from the concentration of energy at the surface, where wave interactions, current effects, and nonlinear processes combine to produce a localized elevation. Its wavelength is relatively short, and its form is steep, rising sharply above the surrounding sea. The speed of a rogue wave is tied to the waves that compose it, moving with the same general flow as the surrounding surface patterns. It does not traverse entire ocean basins as a single coherent structure. Its existence is brief and confined, forming and dissipating within a limited area. The energy involved is concentrated into a smaller region, creating a pronounced peak that stands apart from nearby waves. Confusion between these two phenomena can arise from their shared ability to produce sudden increases in water height. Observations made without detailed measurement may focus on the immediate appearance, where a large body of water rises unexpectedly. Without context, this similarity can obscure the fundamental differences in origin and behavior. The distinction becomes clearer when considering scale and formation. A tsunami is a large-scale event initiated by geological processes, affecting extensive regions and evolving over long distances. A rogue wave is a surface phenomenon shaped by the dynamics of the ocean itself, appearing within existing conditions and passing quickly. In this comparison, the ocean reveals two pathways to elevation, one rooted in the movement of the earth beneath it, the other in the interactions that occur across its surface. Each follows its own set of principles, producing forms that may appear similar at a glance, yet arise from entirely different processes within the broader system. Below the visible surface, motion extends downward in a pattern that is less apparent but equally important in shaping what appears above. Waves do not exist only as crests and troughs at the surface. Their influence reaches into the water beneath, where particles move in circular paths that diminish with depth but remain connected to the motion above. This vertical structure carries energy through a portion of the water column, linking surface form to subsurface movement. In deep water, this structure can develop fully. The depth is sufficient to allow the wave's motion to extend without interference from the seafloor. The circular paths of water particles become smaller with increasing depth, yet they do not encounter a boundary that disrupts their pattern. Energy remains contained within the wave, moving forward as the form travels across the surface. The wave retains its shape over longer distances, preserving the conditions that allow interactions to occur. This freedom of movement is central to how energy behaves in the open ocean. Without the limiting influence of shallow depth, waves can maintain their velocity and structure, allowing different wave systems to intersect and interact over extended areas. The energy carried by each wave is not confined to the surface alone, but distributed through the upper layers of the water, where it can combine with or influence other waves passing through the same region. As depth decreases, this behavior changes. When the seafloor lies within reach of the wave's motion, the circular paths of water particles become distorted. The lower portion of the wave begins to interact with the bottom, slowing the forward motion and altering the shape of the surface. Wavelength shortens, height can increase, and the wave becomes more prone to breaking. The presence of the seafloor introduces a constraint that redistributes energy, preventing it from remaining fully contained within the original structure. In deep water, the absence of this constraint allows energy to remain mobile and adaptable. Waves traveling from distant sources can carry their energy across large distances without significant loss, arriving in new regions where they encounter other wave systems. These interactions occur not only at the surface, but within the shared subsurface space where their energy fields overlap. The result is a complex environment where motion is layered, with each layer contributing to the overall behavior of the surface. The ability of energy to travel beneath the surface also affects how waves respond to changing conditions. When currents or variations in wind alter the surface pattern, the subsurface structure continues to carry momentum that can influence how the wave evolves. This continuity allows for the persistence of energy even as visible forms shift, supporting interactions that can lead to localized concentrations. Depth, then, becomes a defining factor in how waves develop and interact. In regions where the water is deep The full extent of the wave's structure can exist without interruption, enabling the processes that shape complex surface behavior. In shallower areas, the interaction with the seafloor modifies these processes, introducing limits that change how energy is distributed and how waves appear. Through this layered motion, the ocean reveals a connection between what is seen and what lies beneath. The surface carries the visible expression of energy, while the subsurface structure sustains and guides that energy as it moves. Where depth allows this structure to remain intact, the potential for interaction and variation increases, shaping the conditions under which the surface can produce forms that stand apart from the broader pattern. There is a brief interval, measured not by instruments but by perception, when the surface ahead changes in a way that does not fit the pattern the mind has been following. After hours or days of reading the sea, the eye becomes accustomed to its rhythm, recognizing spacing, rise, and motion as part of a continuous flow. When that continuity shifts, the change is often understood before it is fully seen, a recognition that something within the pattern has separated from it. This moment does not arrive as a gradual realization. It is immediate, shaped by contrast rather than detail. The surrounding waves provide a reference that has been internalized through repeated observation, and against that reference, a single form stands apart. The difference is not calculated, yet it is clear, a deviation that interrupts expectation and draws attention to a point where the surface behaves differently. For those on board, the response begins as an adjustment of focus. The eye fixes on the approaching form, and the body responds through subtle changes in balance and stance. The vessel continues its motion, yet the awareness of what lies ahead alters how that motion is experienced. Time does not slow, but perception becomes more concentrated, narrowing to the interval between recognition and contact. The psychological impact is shaped by this compression. There is little opportunity for extended reaction, and the sequence of events unfolds within a limited span. The mind registers the change, anticipates the interaction, and then transitions directly into the experience of the impact itself. The absence of a longer buildup means that the event is encountered with minimal preparation, reinforcing its distinctness from the surrounding conditions. After the wave has passed, the surface returns to its broader pattern, yet the moment remains defined by its contrast. The surrounding sea resumes its familiar motion, but the memory of the deviation persists. It is not only the physical interaction that is retained, but the clarity of the moment when the pattern broke, when expectation and observation diverged. Survivors often describe this interval in terms that reflect its immediacy. The language is direct, focusing on the appearance of the wave and the sequence of events that followed. The descriptions do not dwell on extended emotion, but on the recognition of difference and the rapid transition into action. This focus reflects how the experience is processed as a distinct event within an otherwise continuous environment. The persistence of these memories can be understood through the way the mind encodes events that stand apart from routine. Repeated exposure to similar conditions creates a baseline, a sense of normal that becomes familiar through time. When an event diverges sharply from that baseline, it is marked more clearly, its details retained with greater precision. The contrast itself becomes part of what is remembered. In the context of the ocean, where much of the experience is defined by repetition and gradual variation, such moments carry a particular weight. They are not frequent, and they do not follow the patterns that are learned through daily observation. Their rarity, combined with the immediacy of their occurrence, gives them a distinct place within memory. Through these experiences, the human perspective adds another layer to the understanding of the sea. Beyond measurements and models, there is the lived encounter, where recognition, response, and memory intersect within a brief interval. The ocean continues its motion before and after, yet within that motion, there are moments that stand apart, carried forward not in data alone, but in the recollection of those who were present when the pattern shifted. There are systems in nature that follow clear cycles, where repetition allows patterns to be traced with confidence, and where change unfolds within boundaries that can be anticipated. The ocean does not belong entirely to that category. Its motion reflects underlying laws that are consistent, yet the way those laws combine produces outcomes that do not repeat in simple sequences. The surface evolves continuously, shaped by interactions that are stable in principle but variable in expression. Human understanding approaches such systems by building frameworks, identifying relationships between variables, and refining models that describe how those variables interact. In the case of the ocean, this approach has revealed much about how waves form, travel, and influence one another. The fundamental processes are known, and the behavior of the surface can often be described within a range of expected conditions. Yet there remains a boundary where description gives way to approximation, where the system's complexity exceeds the ability to capture every detail. This limitation is not unique to the ocean. Other natural systems display similar characteristics, where small differences in initial conditions can lead to outcomes that diverge over time. Atmospheric dynamics offer one example, where weather patterns can be forecast within a certain window, but beyond that, uncertainty increases as interactions accumulate. The motion of fluids, whether in air or water, carries this sensitivity, where the same governing equations produce results that are consistent in form but varied in detail. In such systems, predictability exists in layers. Broad trends can be anticipated, and general behavior can be described with confidence. Yet the exact state at a specific moment remains uncertain. The ocean reflects this layered predictability, where large-scale patterns are understood, but local variations emerge from interactions that cannot be fully resolved in advance. The surface becomes a place where order and variability coexist, each influencing the other. Attempts to extend control over such systems encounter the same limitations. Control requires the ability to influence outcomes reliably, yet in a system where small changes can propagate and amplify, maintaining precise control becomes increasingly difficult. Adjustments made in one part of the system may produce unintended effects elsewhere, as interactions carry those changes through the network of influences that define the motion. Technological advances continue to expand the capacity to observe and model the ocean, improving the accuracy of forecasts and the understanding of underlying processes. These advances allow for better anticipation of general conditions and provide tools for navigating the range of possibilities that the ocean presents. However, they do not remove the inherent variability that arises from the system's complexity. The comparison to other chaotic systems highlights a common theme. Whether in the atmosphere, in fluid flows, or in ecological networks, there are limits to how precisely outcomes can be predicted or controlled. These limits are not failures of knowledge, but characteristics of systems where interactions operate across many scales and where sensitivity to initial conditions shapes the evolution of the whole. In this context, the ocean can be seen as a system that is both understood and open-ended. Its behavior is guided by principles that can be described, yet its specific expressions remain variable. Complete control, in the sense of determining exact outcomes at all times, remains beyond reach, not because the system lacks order, but because its order is expressed through interactions that are too intricate to resolve fully in advance. Within this balance, understanding continues to grow, framed by the recognition that the ocean's unpredictability is not an absence of structure, but a reflection of the depth and complexity of the processes that shape it. Across research centers and computing facilities, representations of the ocean are now built not only from equations written on paper, but from simulations that recreate the movement of water across space and time with increasing detail. These simulations divide the surface into fine grids, allowing interactions to be calculated at scales that were once beyond reach. Each point carries information about wave height, direction, and energy, and as the system evolves, these points exchange influence, forming patterns that resemble the complexity observed at sea. Earlier models simplified many of these interactions to make computation possible. Waves were often treated as independent components, combining in ways that preserved overall structure while limiting the influence of localized variation. Modern approaches move beyond this simplification, incorporating nonlinear dynamics that allow waves to affect one another more directly. In these simulations, energy can concentrate, disperse, and shift in ways that reflect the processes identified through observation, producing results that capture a wider range of behavior. The increase in computational power has made it possible to run these models over larger regions and longer periods, integrating data from multiple sources. Satellite measurements, buoy records, and ship-based observations are combined to initialize and refine simulations, grounding them in real conditions. As the model runs, it evolves from this starting point, projecting how the surface may change under the influence of ongoing forces. Alongside these physics-based models, data-driven approaches have begun to play a role. Machine learning systems analyze large data sets, identifying patterns that may not be immediately evident through traditional methods. By training on historical observations, these systems can recognize combinations of conditions that have been associated with extreme waves in the past. The goal is not to replace physical understanding, but to complement it, providing additional ways to interpret complex data. These techniques offer new forms of insight, yet they also introduce their own constraints. Simulations depend on the accuracy of the data used to initialize them, and any gaps or uncertainties in that data can influence the results. Machine learning models, while capable of identifying patterns, rely on the quality and scope of the data sets they are trained on. If certain conditions are underrepresented, the model's ability to recognize them may be limited. Despite these challenges, progress is evident in how well models now capture the general behavior of the ocean. Simulated wave fields can reproduce distributions that align closely with observations, including the presence of occasional extreme peaks. The representation of interactions between waves and currents has improved, allowing for more realistic depictions of how energy is redistributed across the surface. At the same time, the limits of these models remain visible. The ocean's complexity means that even detailed simulations cannot account for every interaction at every scale. Choices must be made about resolution and scope, balancing the desire for precision with the practical constraints of computation. As a result, models provide an approximation of reality, one that becomes more refined with each advancement but does not fully encompass the system. In this evolving landscape, modeling serves as a bridge between observation and understanding. It translates physical principles into dynamic representations, allowing the behavior of the ocean to be explored in ways that extend beyond direct measurement. Each improvement brings the model closer to the surface it seeks to represent, while the remaining differences highlight the depth of complexity that continues to define the ocean's motion. At first glance, the open ocean often appears uniform, a continuous surface where variation unfolds within a narrow and familiar range. The motion seems steady, shaped by patterns that repeat with enough consistency to suggest stability. Yet within that apparent steadiness, there exists a deeper structure, one that carries the potential for outcomes that do not align with the surface impression. Rogue waves emerge from this underlying structure, not as isolated anomalies, but as expressions of processes that are always present. The same interactions that produce ordinary waves also allow, under certain conditions, for energy to gather in ways that exceed the surrounding pattern. The difference lies not in the introduction of a new force, but in how existing forces combine at specific moments and locations. This reveals the ocean as a system that is continuously active beneath its visible layer. Energy moves through it in multiple forms, intersecting and redistributing in ways that are not always apparent from observation alone. What appears calm can still contain a complex arrangement of motion where waves of different origins pass through one another, carrying histories that extend beyond the immediate scene. The idea of a living system becomes useful here, not in a biological sense, but as a way of describing something that evolves continuously, responding to internal and external influences without settling into a fixed state. The ocean adjusts to wind, currents, and distant disturbances, integrating these inputs into a surface that is always in transition. Within that transition, the potential for variation remains embedded, even when the visible expression is subdued. Rogue waves highlight how extremes can exist within this continuity. They do not require exceptional external triggers in every case, but can arise from the alignment of ordinary processes. This alignment is temporary, forming a peak that stands above its surroundings before dispersing back into the broader pattern. The surface returns to its prior state, but the event reflects a capacity that was present all along. The contrast between appearance and potential becomes more apparent through this lens. A calm surface does not indicate the absence of energy or interaction. Instead, it reflects a moment in which those interactions are distributed in a way that produces moderate variation. The underlying processes continue, and within them, the conditions for more pronounced outcomes remain possible. This perspective shifts how the ocean is understood. Rather than viewing it as a surface that occasionally behaves unpredictably, it can be seen as a system where variability is inherent and where the range of possible states includes both the familiar and the extreme. The visible pattern represents only a portion of what is occurring, a snapshot of a system that contains more complexity than can be observed directly. The presence of rogue waves serves as a reminder of this complexity. They illustrate that the ocean's behavior cannot be fully inferred from surface appearance alone, and that even within stable conditions, there are processes at work that can produce significant variation. These events do not stand apart from the system, but are integrated within it, arising from the same dynamics that shape every wave. In this way, the ocean reveals itself as a continuum of motion, where calm and intensity are not separate states, but points along a spectrum defined by interaction. The surface carries the visible expression of that spectrum, while beneath it, energy moves and reorganizes, sustaining the potential for change within every moment of apparent stillness. Long stretches of open water can pass without interruption, the surface moving within a range that feels familiar and contained. The horizon remains steady, and the patterns that cross it seem to follow a quiet order. Yet within that order, there is always more at work than the eye can fully register, a depth of motion that continues beyond what is immediately visible. Rogue waves have shown that the ocean is not defined only by its typical behavior, but also by its capacity for sudden change. These waves do not exist outside the system, nor do they arrive from elsewhere. They form within the same processes that shape every rise and fall, emerging when those processes align in a way that concentrates energy into a single, brief expression. Their presence does not contradict the ocean's usual patterns, but reveals how much those patterns can contain. This understanding reshapes the sense of scale. The ocean is vast in size, but also in possibility, holding within it a range of outcomes that extend beyond the average conditions often observed. The surface can appear calm, even uniform, while beneath that appearance, interactions continue to unfold. Energy moves, overlaps, and reorganizes, carrying with it the potential for variation that is not always apparent. Despite advances in observation and modeling, much of the ocean remains beyond continuous measurement. Large areas are still only partially observed, and many interactions occur without direct record. Instruments capture fragments of the whole, building a picture that becomes clearer over time, yet still incomplete. What is known continues to expand, but it does so alongside an awareness of how much remains unobserved. Rogue waves exist within this space between knowledge and uncertainty. They are no longer considered impossible, and their occurrence has been documented across different regions and conditions. At the same time, the exact circumstances that lead to their formation cannot always be identified in advance. The processes are understood in principle, yet their specific alignment remains difficult to anticipate. In this balance, the ocean invites a different kind of attention, one that holds both understanding and openness. The surface offers a continuous display of motion, while the deeper structure carries interactions that shape what appears. Each moment reflects a system that is active, responsive, and capable of outcomes that extend beyond the immediate view. There is a quiet awareness that can emerge when looking across open water, a sense that what is visible is only part of a larger process. The patterns are there, moving steadily, yet they are not fixed. They shift, combine, and evolve, carrying within them possibilities that may not reveal themselves unless conditions align. If this kind of exploration resonates, there are many more paths through the ocean's story that unfold in the same quiet way, each one offering another view into how the natural world organizes itself beneath the surface. A simple gesture of support helps these stories continue to reach further, connecting with others who find interest in the same slow unfolding of science and observation. And if you choose to stay, there is always more to follow, more moments where the surface gives way to deeper understanding and where the familiar reveals something that was there all along, waiting to be seen.